Well, a warm welcome indeed to anyone here. Thank you for joining. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem involving current. These are called rate problems. A lot of times you'll see problems where there's some wind and usually a plane or some kind of device to travel in, some kind of transportation vehicle, is going one direction with some resistance and is coming back, being helped by that current or stream or wind or whatever it is. And so, of course, if you've ever, run uphill, for example, it's harder to run uphill. And if you've run downhill, it's a little easier, especially if you're on a bike. What we need to start off with is this main equation, which is the rate describes how quickly the position is changing over time. So a lot of times we'll write this: rate equals distance over time. Or sometimes we'll write it as rate multiplied by time. You can see that you can just multiply the time on both sides of the equation, and that will give you the overall distance. And we know this to be true. For example, if I tell you I'm driving 3 miles per hour for 7 hours, you just multiply those and you get the total distance, right? So here we don't know the speed of a man rowing a boat. We know how long it takes him to go upstream, which is a 6-kilometer path in 2 hours to see a friend in town. But then when he rows back home, downstream, it only takes him 80 minutes. So go ahead and pause the video, give yourself about, 5 or 6 minutes to try to work this out. And then when you're ready, unpause the video, come back, see how we did it here. Right, so we're going to need some variables to represent the situation. But we're also going to need to break this journey into two parts. We want to have the upstream part. This is going to be with some resistance. And then we want the downstream part. This is going to be getting help from the current. So what we want to make clear is, how fast is this person going? Well, we'll just call it B for boat. That's how fast he's going, but we need to subtract the current. So if he's going 4 miles per hour or whatever, but the current is pushing back 2 miles per hour, we would have to subtract those. Or 4 miles per hour and pushing back 1 mile per hour, we would have to subtract those. On the other hand, when he's going downstream, we're going to take the speed of his boat and we're going to add the speed of the current. It's going to help him out. Let's get the time going. And let's get the distance going. Now, in these problems, one key to solving them is identifying which of these two quantities is remaining the same. The problem can be phrased in different ways. The situation can be presented in slightly different ways. In this case, we're assuming that the man's taking the exact same path, which means the same distance is covered. 6 kilometers. I didn't even have to say 6 kilometers on the way back. I just said he rows back home. It's pretty obvious that if he went 6 kilometers to get away from home, he's coming back with the same distance. This is the thing which is constant in this problem. Okay. In other situations, the time might be constant. So what we need to do is we need to kind of figure out, how do we represent the time? Well, if we use the rate equals, or rate times time, rather, we use the rate times time equals distance equation and manipulate it even further, we figure that the time is equal to the distance over the rate. So let's see, that means that we have 6 as the distance, and depending on what the rate is, if it's B minus C multiplied by the time, or if it's B plus C multiplied by t2, either way, the total distance is going to be 6. All right. Now we can use the time that we are given. We're going to have to convert some things if we want it to be in hours or if we want it to be in minutes. So let's keep it in hours, I think. Going upstream, it's going to take 2 hours. And going downstream, it's going to take 80 over 60. That's 80 minutes over 60 minutes, which gives us 4/3 of an hour. Okay, well now we can make some use of this. Yes, indeed. Since both of them multiply to 6, we're going to have that b minus c times 2 equals b plus c times 4/3. This gives us a system of equations, right? So we have 2b minus 2c equals 6, and we have 4/3 b plus 4/3 c also equals 6. Once we've represented this as a system of equations, I think it's very clear how to proceed from here. We really just want to provide some kind of coefficients that will cause elimination. You could also do substitution here, but I think it's a little easier to do elimination, and it's also good practice to do elimination. So let's take this equation, and let's just multiply everything by 3. So we get 4b plus 4c equals 18. That's kind of nice to work with. And then if we multiply this top equation simply by 2, we get 4b minus 4c equals 12. Okay, so here we're able to cancel out these opposite terms, leaving us 8b equals, add them together, 30, and that means that b is equals to, if you don't know how to divide by 8, I mean you should know how to divide by 8, but dividing by 8 just means you're dividing by 2 3 times in a row. So 30 divided by 2 is 15, 15 divided by 2 is 7.5, 7.5 divided by 2 is 3.75. You could just call it 15/4 as well. If you were reducing this fraction as much as possible, you can only reduce it by 2. So 15/4, that's the decimal version, which means the boat is going 3.75 kilometers per hour. Great. Now, if that's the case, we still need to figure out how fast is the stream's current. We found out how fast he would travel in still water. That's the rate of just the boat. But we need to go a little further than that. We need to figure out how fast is the current. Well, we can easily plug this in to any equation here, really. I think I'll just use the one with a positive. Why not? So we'll say 3.75 plus c times 4/3. Oh, actually, maybe I want to use the top equation just because it's times 4/3 versus times 2. It's a little bit easier to multiply by 2. Let's use the top equation. My apologies. We'll have 3.75 minus c times 2 equals 6. So that means we have 3.75 minus c equals, we'll just divide both sides by 2, don't distribute, equals 3, which means 3.75 equals 3 plus c, and then we get 0.75, or 3/4 if you like, equals the speed of the current. So the current's going pretty quickly, 3/4 of a kilometer per hour. It's not super fast, but it's definitely not slow. And with that information together, we have the speed of the boat in still water, meaning with no current, this is how quickly it would travel. And with the current, we have 0.75 kilometers per hour. Now you notice that if I were to travel in still water at this rate for 2 hours, how far would he actually go? He travels 7.5 kilometers. But because there was a current, it only went 6 kilometers, which is 80% That's 3.75, and 80% of 3.75 is 80% of 7.5 is how far he actually went. So 80% of this rate is how fast he actually went, due to the current slowing him down. Okay, well, that was a pretty quick problem, but in general, you're going to want to solve these rate equals distance over time problems by making some kind of a chart. A lot of times we will have two unknowns. The only way you can solve an equation with two unknowns is if you have two equations. So just keep that in mind. I think that's enough blab out of me. I'll see you guys next time.